Most elements have atoms with different numbers of neutrons. These atoms that differ in only the number of neutrons are often called isotopes. In some textbooks they call them nuclides. Here we see two isotopes of the element copper. Copper has two isotopes, copper 63. Remember, to the left, superscript, the number means the mass number, the total number of neutrons and protons. Copper 63 has 29 protons because that's what all copper atoms have. Also 29 electrons, and 63 minus 29 or 34 neutrons. Copper 65 has two additional neutrons. That is 29 protons, 29 electrons, but now 36 neutrons. These two forms of copper atoms, as you see, they differ only in the number of neutrons. If we used a sample of copper in an experiment, the copper would be made up of copper 63 and copper 65 atoms or isotopes, and the atomic mass of the group of copper atoms would be the weighted average of the isotopic masses of copper 63 and copper 65. Now, if we know the relative abundance of the two isotopes in percentage terms, we could calculate the overall atomic mass that the sample of copper would exhibit. Now, it happens from mass spectrometric measurements that we know that copper atoms, 69.1%, 17% of all copper atoms are copper 63. So since there's only two isotopes, we can subtract that number from 100% and find that 30.83% are the other isotope, copper 65. So if we'd like to calculate the atomic mass of copper in the sample, it would be done using the weighted average formula. That is to say, the decimal fraction amount of copper 63 times the copper 63 isotopic mass is the contribution of that isotope, and that's added to 0.3083, which is the decimal fraction equivalent of 30.83%. Times its isotopic mass would be the contribution of copper 65, and those two summed together would give the atomic mass of copper. So if we put in the numbers, 0.6917 abundance decimal fraction times 62.9396 the isotopic mass in AMUs of copper 63, and then we add that to the same thing done for copper 65, its abundance in decimal fraction 0.3083 times its isotopic mass, which is 64.9278, gives the two contributions of the isotopes to the overall atomic mass. The first one, copper 63, being 43.54, the second one being 20.01 for copper 65, and that adds up to 63.55, the weighted average atomic mass for the overall sample, the large sample of the copper atoms that we're going to use in the experiment. Now, this is reflected in the periodic table. The entry for copper has, of course, the atomic number above the symbol Cu, and below the symbol is the weighted average atomic mass. So whenever you have the necessary information, and that is the abundance of each isotope and the isotopic masses, you can use the weighted average formula here to calculate the number that represents the overall weighted average atomic mass of copper. And of course, this being like any other algebraic equation, if you know all but one of the terms, you can calculate the missing one.